Okay, and shortly will open. I open this window. You can always click that off and it won't show that dialog box anymore. I'm just going to cancel it. I'm going to start with a blank sheet. I'm going to say open data. Okay, and I'm going to open a file that already exists. Say the file's on my desktop. I know that because I just saved it there. And I know that that file is an Excel file. So I'm going to tell it to look for Excel files. And sure enough, there's my Georgia student survey as my Excel file. Okay, I'm going to click that file and I'm going to say open. SPSS is going to look at that file. It's going to realize it's an Excel file. It's going to say, okay, the data goes from row A1 from cell A1 to cell Q60. In other words, columns A through Q, rows 1 through 60. That's where what's on that worksheet. That's the data. That's what it plans on importing. It also has checked off, should I read the variable names from the first row of data? Now, you and I know that the first row of data was, in fact, the variable name. So I'm going to leave that as is. I'm going to leave that checked. Okay, so now here it is imported into Excel. Now I can't work with this like in Excel. I can't add this column up or do any of this kind of stuff. This is really just a database. It's just a list of all this data. I can go into my variable view and I can see each one of these columns represented as a row. So like for gender, if I wanted to, I could go into gender and tell it, well, gee, the value 1 represents male and the value 2 represents female. Oops, I think it was 0. 0 represents female. Okay, I'm not sure that's the case because we don't have our code book available, but if I go back now to data view, I can see that it's substituted male and female for all of those numbers. Okay, so now the part that I'm interested in is college grade point average. Okay, so I'm interested in descriptive statistics for college grade point average. To do analysis for grade point average, I can say analyze. Naturally, start off almost any analysis with analyze. Can you guys see analyze at the top of my screen? Because sometimes I find that when I broadcast on GoToMeeting, you can't see the stuff right at the top. You guys can see it? Okay, good. Analyze. Then I'm going to go down to what seems like the best selection, which is descriptive statistics. Now, as we've seen in class, if I go into frequencies, frequencies just means counts. That's good if I want to know the number of males and females, number of redheads, brunettes, blondes, and so on and so forth. Nominal data doesn't help me so much with numerical data, which we want to work with right now, which is the grade point averages. Descriptive statistics, descriptives is means, medians, and so on and so forth, but it's limited. It doesn't give me everything I might want to know. It gives me a summary of some descriptive statistics, but if I actually go into Explore, it gives me more descriptive statistics. It gives me more detail on the descriptive statistics. So I'm usually going to go straight to Explore rather than use descriptives or frequencies. So if I go into Explore, the other advantage of Explore is it gives me an opportunity to factor the data into different groups. For instance, if I use descriptives and look for college grade point average, I can only look for grade point average for all students, mean, median, mode, for all students, standard deviation for all students. Explore lets me look for it for all students, or if I want, it also lets me factor it or break it up into groups like males or females, or students that are working or not working, and so on and so forth. So I'm going to go into Explore instead. Brings up a box that allows me to tell it in the dependence list what is the variable that I want to find the descriptive statistics for. And we know, as we said, I'm not even sure if this is really what the problem asks for, but I'm going to work with this instead. Anyway, college grade point average. So I'm going to move that into the dependence list. So now, if I click on these various buttons, statistics, it's already checked off to give me descriptive statistics. Plots, if I click on that, it will always give me, by default, box plots. So that's why you don't see box plots in here. It's right now it's checked off to give me stem and leaf diagrams. Maybe I don't want that. I'm going to uncheck that. Give me histograms instead. I'm going to say continue. Okay, there are some other options like what to do if you have to exclude cases and stuff like that, if there's missing data and so on. I'm not going to worry about that for right now. The other options I got down here is to display statistics, descriptive statistics, and plots, or plots, or display both. I want it to display both when I do the output. So I'm going to go ahead and do this analysis and say OK. Okay, by the way, just so you know, if you are falling asleep, have other things to do, you need to get on to other things. If you need to leave, don't feel free to leave. This is completely voluntary. I'm not keeping any attendance other than just trying to keep track of, the total numbers of people that I'm getting and stuff like that to see, when this is working well, when it isn't working well. But I'm not keeping track of like specific attendance or anything like that. So if you want to leave, you can just, if you want to say goodbye, you can say goodnight, you can, but you don't have to announce yourself coming in or out, at any point when I'm holding one of these. Okay. So let me go back here to, okay, let's see. I just got to get some stuff out of the way here now that I clicked on a couple of things. Okay, so I'm back. All right, so let's see what it gave me. It gave me that the mean grade point average was 3.6. Well, these guys are pretty smart. Okay, confidence interval we're going to learn about later on. I'm not going to worry about that too much. I got the median, okay, 3.75. Median was a little higher than the mean. Very interesting. Variance, standard deviation, minimum, maximum, the range, the interquartile range, right? We can talk about that a little bit. Okay, so let's take a look at what this distribution looked like. Whoa, look at this. This part over here at the right side kind of looks like a normal distribution to some degree, but then there's a few people that had relatively low grade point averages here, right? So this distribution looks like it's skewed to the left. There are some people with low grade point averages that are skewing, pulling the average, the mean, away from the median, pulling it to the left or lower. And in fact, if I look up here, I can see that the mean is lower. It's 3.6 compared to the median, which is 3.75. And if I look at the box plot, I get the same result. The median is higher. And there are values pulling the average down. So the median is up towards the top part, and there's more values. There's a greater weight below. Okay, this median should have been right in the middle. This whole thing should have been in the middle of these feathers. And we got a few people that I even might be considered outliers, by SPSS. That's technical outliers. SPSS does basically a calculation. If more than one and a half standard deviations above the 75th, I think above the 75th percentile, it starts to consider you an outlier. Or you can change that if you want in SPSS, but for our purposes, these numbers are a bit extreme compared to the bulk of the other data. We can just look at it this way. But you can see this is kind of skewed to the left. Okay, so now one of the things I can do is I can go back into descriptive statistics, explore, and I can go in here and I can say, let's factor this by gender. Let's separate it into males and females. And I'm going to leave all the functions the same. And sure enough, now it gives me data for females, for males. It gives me a histogram for females, a histogram for males. And it gives me side-by-side box plots for males and females. Okay, and the way it looks here, it looks like most females are doing better than most males. So you know what that means. That means obviously that I reversed the 0 and 1s because I don't believe that result. I know most of you don't either. So at any rate, this I can get all of these outputs from SPSS very quickly. I could get all of these descriptors from Excel as well, but take a lot more work. Okay, so and we know I can just click on any of these tables, charts. I can copy and paste them into a Word document. Okay, so I'm not going to spend too much time on that, just so you can see that working. You can use R to do the same thing. Okay, presumably we'll give you the data in a format that'll won't trip you up too much, right? And you'll interpret the data. You'll interpret the data appropriately. Okay, so now let's see. Take a look. Before I go any further, is there something? Because I plan on going for another 15, 20 minutes. We're up to we're over an hour already, so I plan on going for maybe an hour and a half, so maybe another 15, 20 minutes. Is there something that you guys, should I continue going through this stuff in general, or is there something specific that you would like me to go through? I'll give you a moment. I'm gonna pull up the homeworks next. Okay, can I go ahead? I don't see any. I know. I can see you guys are there. I can see the list that there's still 11 of you there, and binomial distribution. Okay, good. That's a good point. Okay, so now binomial distribution and Poisson distribution. You guys recall that we had a situation. We had. Let me see if I got something in here that might be reminiscent of that. Let's see, homework. There's problems. Let me see if there's something in this homework. Yeah, I guess this is the lab we went through where we brought it up. I think I might have something else here too. Homework 1. Assignment 1. Let's try assignment 2. Nope, not really. I want to hold that up because I want to do something quickly with age adjustment. Okay, I'm going to pull up Excel first. I'll make up my own example. Okay, you guys recall when we talked about probability of events occurring where there were two possible outcomes. You come across that quite a bit. Disease, not disease, old, young, male, female, obese, not obese. There's a lot of data that you can describe as either being one of two states, 0 or 1, yes or no, true or false. Okay, so I'm going to look just at a coin toss. Coin toss. Let's say I cost a toy and I could get a heads or I could get a tails. Right? If I toss a second coin, well, that second toss, the first coin was heads. The coin doesn't know what the first one was. I could get a tails or a heads as a result of that one. Right? Third coin that I toss, well, depending on if I got a tails or a head, I could get another tails or a head, or I could get a tail or a head if I had gotten a head also. Well, what happens is that all of these possibilities multiply so that you could have heads, tails, tails, heads, 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 tails, head, tail, tail. There are many possibilities as for all these independent events. So if we were looking at how do I get 10%? Okay, I'm going to pull that one up for sure. Let me get through this explanation. If I were looking at independent events like coin toss, if I asked if you, since it's independent, if I asked you what was probability to get all heads, it'd be 0.5 times 0.5 times 0.5. Okay. If I asked you what's the probability of getting exactly 2 heads out of 3 tosses, that gets complicated because one way is to get heads, heads, tails. Another way is to get tails, heads, heads. Another way is to get head, tail, heads. There's a lot of different ways out of all the different possibilities to get that. So we can represent that those random probabilities with the binomial distribution. For instance, if I told you the probability that a person was diabetic, that a person had high blood pressure in a population was 21.21, was 21%. 21% of the population has high blood pressure. P equals 0.21. If I told you that you work for a clinic where you have a rolling medical clinic that has outreach in the community, and you can see 100 patients a day, and you want to bring with you enough supplies to make sure that you can start initial treatment and give out literature for patients that you anticipate are going to have high blood pressure. Okay, well, if you're going to take 100 patients, and in the population that the prevalence is 21%, that you're going to expect 21 out of those 100 to be to have high blood pressure. That's the most likely outcome because the prevalence is 21%. You got 100. You're going to look at 100 people, random people that are going to come into your facility. Okay. Now, let's say you decide I'm going to bring 30 kits with me for treating high blood pressure. Okay. What's the probability that you will get 31 or more patients that have high blood pressure? Okay. Well, let's see. What's the probability? Well, the probability is going to be equal to the binom dist, right? Parentheses. Okay. The number of successes. What's the number of successes? Well, what's the probability that you won't exceed 30, or that you get 31 or more? Probably you get 31 or more, right? Well, I'm going to look at the probability of getting 30 or less, because the binom dist, like our z table, works downwards only. So I'm going to look at the probability of getting 30 or less. 30 successes out of 100 people with a prevalence of 0.21, a probability of 0.21, and I'm going to say true cumulative. The probability that we'll get 30, 29, 28, 27, 26, or 3, or 4, or 2, or 1, or 0 out of 100 patients that have high blood pressure is 98.7%. So what's the probability that you'll get more than 30? Well, it's equal to 1 minus that 98.7%. Okay, so the binomial distribution, if I use the formula in Excel for binom dist, it gives me an opportunity to look at all the probability for all these outcomes, given that you know what the prevalence or the probability is, and that you know the number of tests, the number of successes, and that you use the term true or cumulative correctly. Now, if I had written true over here, right? If I had written false instead of true, it would, for cumulative, it would only give me the probability for exactly 30 out of 100. That doesn't seem very likely that would get exactly 30 people out of 100 that had high blood pressure on any given day. And in fact, it's a very small possibility. It's less than 1%. Okay, does that help? Okay, I'm going to go to question 8A from the last lab class. Okay, okay, question number 8. A study indicates that 10% of nursing home patients are diabetic. You randomly select 10 patients. What's the likelihood that exactly one will be diabetic? Okay, we're going to take that and we're going to go over here. Exactly one. Okay, what's the probability? Probability is going to be equal to binom dist, parentheses, number of successes, number S, 1. Number of trials is 10. The probability is 0.10, 10%. And exactly 1, since we're saying exactly 1, we're going to say false for cumulative. So the only correct answer is going to be exactly 1 out of 10 people. And the probability is 38%. 2 or less will be diabetic. 2 or less. Okay, so how am I going to phrase that? Equals binom dist, parentheses, and number of successes. So 2 or less means 2, 1, or 0. So that's going to be 2 successes, comma, and everything below it, because we're going to say true now, out of 10 trials, 10 people randomly selected. 0.1 is the probability of any individual being diabetic, comma, except this time I'm going to say true, and that's going to include 2, 1, and 0, 2 or less. That's 93%. So next, I'm going to see more than 4 will be diabetic. More than 4 will be diabetic. Well, what satisfies more than 4? More than 4 is 5, 6, 7, 8, 9, 10, right? It doesn't include 4. So, but I can't go that direction. I can only go down. If I go in here, more than 4, if I go in here and say equals binom dist, watch this trick, okay? Number of successes, I'm going to put 4 in there. Then I'm going to put 10. Then I'm going to put 0.1, just like before. Then I'm going to put true. parentheses. Now, before I hit return, this is going to give me the probability of 4 out of 10, 3 out of 10, 2 out of 10, 1, and so on and so forth. It's not going to give probability for 5 out of 10, 6, 7, 8, 9, or 10, right? Everything from 4 down, including 4. So the probability of that occurring is 0.998. So what's the probability that more than 4 will occur? Probability that more than 4 then occurs is going to be equal to 1 minus this. What's left, in other words, okay, after you got rid of the probability for 4, 3, 2, or 1. Right? A little tricky, right? A little tricky in terms of words, but if you read it carefully, 4 or more than 4, how about 4 or more? Well, 4 or more, you see the difference there? 4 or more, what's the probability 4 or more? 4 or more includes 4, but doesn't include 3, 2, 1. So this time it's going to be binom dist, parentheses, 3 comma 10 comma 0.1 comma true, close parentheses, and the difference is going to be equal to 1 minus this number. Okay, this number represents now, if you look up here, it represents 3, 2, 1, and 0. So 4 or more is going to be what's left from 3 after 3, 2, 1, and 0 is subtracted from a probability of 1. Okay, does that make sense? Did that help? Okay, person that asked that? Okay. 10%. Question 8A. Exactly what did I get on 8A? Let me see what I got on 8A. First one I got, did I get 10%? I'm not sure. How did I get 10% on 1? In class, I said it was 10%. And why didn't you people correct me in class when I said it was 10%? Oh, no. You know what it was? Maybe you misinterpreted me, or maybe I misspoke, because what I was suggesting that if we take 10 people, if the prevalence is 10%, right, then we are saying that 10% of the patients are likely to have diabetes. So the most likely outcome would be one diabetic patient, but not that the probability, if we took a random sample of 10 people, that the probability of getting exactly one would be 10%. Maybe I misspoke it, or I didn't. Uh, 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 I'll blame it on me. It's not you, it's me, probably, right? Might as well. Okay. Um, um, I don't. Yeah, be honest with you, I don't remember why I would have said it. The only thing I can think of is that I was trying to describe that the most likely outcome would be that 10% of any sample that you took. Like if it was 100, since the prevalence is 10%, if you had 100 people, the most likely outcome would be 10 out of that 100 having diabetes if the prevalence is 10%. That's different than saying what's the probability of getting it exactly 10 people out of 100 if you randomly sampled it. Okay, in fact, let me do that. Right, let's see what the probability of that would be. Equal binom dist, parentheses, and what's the probability of getting exactly 10 people out of 100 if the prevalence is 0.1, comma, false. Exactly 10 people, and that would be 13%. Right? A little bit different than, a little bit higher than 10%. But then you have all those other possibilities that would have to be accounted for. 9 out of 100, 8 out of 100, so on and so forth. Okay, 10 and 11. Okay, now 10 and 11 is something called a Poisson distribution, I think. Let me start with 10. Number of traffic accidents occur in a particular stretch of road during a month follows a Poisson distribution. Up, here you gave away the farm there. If you say that in there, you're giving away the farm. But if we didn't say that, has a mean of 9.4 with a probability that less than 2 accidents will occur. Find the probability that I'm going to say less than, I'm going to change that. I'm going to say less than 6 accidents will occur on a stretch of road during a randomly selected month. Okay, what's the probability that that's going to happen? Okay, that less than 6 accidents when it's an average of 9.4. Well, we're talking about, again, accidents. Either you have an accident or you don't have an accident. However, this is looking at it from the number of accidents over a period of time, a temporal relationship, a time relationship. Okay, that's kind of a dead giveaway for Poisson distribution. Okay, since it's a random event. Okay, so I'm going to take a look at this. I'm going to say over here, the happens to be a function equals Poisson. Okay, and it works, dot this, parentheses, it works very much the same way that the binomial distribution worked. Okay, X is the number of events that we are testing. What's the probability of having six, I'm going to say six or fewer, less than six accidents. What qualifies as less than six accidents? What's the highest number of accidents that qualifies as less than six accidents? Somebody tell me. Five, right? Less than six accidents means five. Okay, so five, what's the probability you have five or fewer? Less than six accidents, comma, given that the mean number of accidents is 9.4 during that period of time. And I'm going to say true for cumulative because we're saying what's the probability of less than five? Not five exactly, but less than five, less than six. 5, 4, 3, 2, 1, 0 accidents. Hit enter, and the probability of having less than six accidents, in other words, five or fewer, during a given month is 9%. Okay, that's the way we would use the Poisson distribution. Okay, so let's take a look at somebody about number 11. Suppose that 20% of the individuals, 20% of individuals 85 years or older, I guess, suffer from dementia. You go to a nursing home that's been feeding residents a diet consisting of natural, organic, and healthy foods, so on and so forth. You find that 15 of the residents who are 85 years and older have Alzheimer's. What is the likelihood of this outcome based on your expected rate of 20%? Okay, let's take a look at this. Here's a binomial distribution. You have either they have Alzheimer's or they don't have Alzheimer's, right? So we're dealing with a population, we would expect 20% of the population to have Alzheimer's, okay? And we're looking at 100 residents, okay? 100 residents. Okay, so now, let's see, 20% of 100. I think I should be seeing most likely number, n times p, most likely number, or the mean number that I would expect to see if I sampled over and over again nursing homes that had this population of patients. I would normally expect to see 20 out of 100 patients that I sampled in each one of those nursing homes to have Alzheimer's. In this case, only 15 of them have Alzheimer's. Well, what's the probability that, given that the real situation is 20%, what's the probability that you get 15 or fewer patients that have Alzheimer's? Okay, well, let's use our binomial distribution. Parentheses, okay, the number of successes in this particular place was 15, comma, out of 100 people sampled. Probability is 0.2, comma, and we're going to say true because we want to know the probability of getting 15 or fewer. Probability of getting 15 or fewer is 13%. It's not that small, right? So in other words, in this case, we went into this nursing home and we found that because they were feeding them like this cockamamie free range chicken, omega eggs, flaxseed, whatever. I'm sure the residents hated this. 85. They're from like the 50s, 40s, and 50s and stuff like that. They like meat and potatoes. They don't want this stuff, right? They're probably pissed off, assuming they have teeth and they can eat the stuff. They would rather have a steak, right? So you're feeding them this stuff, and you find that like only 15 out of 100 instead of your expected 20 out of 100 have dementia. You say to yourself, well, gee, how remarkable is that? Well, this is going to happen. You're going to get this result in 13 out of every 100, or 13% of the nursing homes that you sample 100 people in, where the prevalence is 20%. You're going to get a number as low as 15 or lower 13% of the time. It's not that rare to get that number, to get a number less than 15. Remember, you're not going to go into every one of these and get exactly 20 out of 100 if the prevalence is 20%. Sometimes you get 18, sometimes you get 31, sometimes you get 12, something, out of 100, but the prevalence overall will still be 20%. So it's not that rare. If they had been 10, let's take a look at what's the probability if it had been 10 out of 100. Well, that's less than 1%. Well, if you had gone in there and got only 10 out of 100 that had dementia, you'd say to yourself, gee, that looks like a pretty rare event, less than 10 or less out of 100. Maybe that diet is really working. Does that help at all? Did that make things a little bit clearer? Okay. I think I want to end up with one more thing, and that is the age adjustment. Okay. And the age adjustment, I got a couple of quick examples. We're going to running a little bit long here, but a lot more stuff to cover than I had realized, right? Always is. Always seems to be the case. Okay, I'm going to get this out of the way. Then I'm going to go back over here, and I'm going to, let's see, age adjustment. Well, first of all, why do we do age adjustment? Age adjustment. How about this thing? What's this? Oh, okay. I want to do that one second. Age adjustment. I had one. I had another one here. I want to find. Age adjustment. Oh, okay. Let's take a look at this. Actually, I think I want the other one. I want this one. I want the other one. Try the other one. Okay, let's start with. No, I think I want the other one. That doesn't much matter. I'll start with this one. Okay, let's take a look at this. Now, I got two cities. In each one of these two cities, right, they have the same age-specific death rates. If you're less than 20, your chances of dying are 1 in 100. 21 to 40, your chances of dying are 3 out of 100, 3%. Over 80, your chances of dying are 10%. Both populations, City A and City B, have the same age-specific death rates. Both populations have a population of 1 million people, right? Okay, now I'm going to calculate the number of deaths we would expect if they're dying at the rate of 1% times the population in that age group. We'd expect 2,000 deaths in that age group, and then I'm going to go fill down and calculate all the number of deaths in these other age groups, get the total. Okay, and from this population in a year, we would expect 35,000 deaths. In this population, I'm going to do the same exact thing. It's going to be your rate in that age group times your population in that age group is going to be that number of deaths, and I'm going to fill that down, and we'll get the total number of deaths for each one of these age groups. And then I'm going to get the sum, parentheses, and total number of deaths, and that's total number of deaths. So for City A now, I'm going to calculate a crude mortality rate. My crude mortality rate is equal to the number of deaths divided by the total population. Okay, it's 0.035. Another way of expressing that would be to multiply, I'm going to multiply by 1,000. To multiply by 1,000, it's going to be that times 1,000. Okay, in other words, 35 deaths per 1,000. Okay, that's all you're doing when you do that per 1,000 or per 100,000. You're just multiplying it out so you don't have to deal with fractions, you just deal with whole numbers. Let's take a look at the crude mortality rate for City B. It's going to be equal to 48,500 deaths divided by population of 1 million again. That's what we get. I'm going to change that into per 1,000. This times 1,000 is the death rate per 1,000. It's 48.5 per 1,000. Uh-oh, what happened here? Everybody's dying at the same rate here as they are here, but my crude mortality rate for City B is almost half again what it is for City A. You guys see what happened there? You see why that's what clearly what happened there? Anybody know what's the difference? Why did I get a higher mortality rate for City B than I did for City A? Somebody volunteer me a reason. Why would I get a higher number here? Well, look at this. If I look at the distribution of this population, There's 200,000 people that are less than 20. There's only 100,000 less than 20 here. There are 200,000 people that are 61 to 80. There's 400,000 people in that age group there. So even though the population is the same overall, the distribution of the population is different. So that population city A, I have a younger population than I do in city B. So even though the age specific death rates are the same, right? What ends up happening is I have more deaths in this population because it's an older population and they die, their death rates are higher. It's because there's more, even though there's no difference in the death rates within the age groups, right? And that they're both as healthy, the cities are equally healthy. I get a higher death rate here simply because it's a much older population than city A. That's a problem. You want to compare, say the death rate in Nome, Alaska to the death rate in Miami, Florida, which has a much older population. Alaska has one of the youngest populations. Well, what you're going to find is that it won't be a fair comparison. It's going to seem like the death rate in Miami is much higher and there's some sort of health emergency going on in Miami, when that may not be true. What is true is just an older population, so you're going to have higher death rates, right? So, but there isn't really a real difference in the health or the within cohorts or within comparable groups in those two cities, right? So I'm going to open up another file here, which I'm going to close that off. Okay, so let's take a look at the comparison of mortality rates due to heart disease for males and females in New York City. This is to some degree legitimate data. Okay, so I'm going to look at the death rate per 100,000 for females in this age group, less than 25. It's going to be equal to the number of deaths divided by the population in that age group. And then I'm going to multiply that by 100,000 times 100,000, just so we get that. Whoops, I wanted my times 100,000 to be outside the next parentheses. Times 100,000, just so we don't have to deal with fractions. Okay, it's 1.69. I'm going to calculate it for all the rest of these as well. Fill down. Okay, and those are my death rates. I'm going to do the same thing. Death rate, age-specific death rates. These are for males in this population is equal to number of deaths over the population in that age group. I'm going to put parentheses around this and multiply by 100,000. Parentheses multiplied by 100,000. Okay, and I'm going to fill down. Fill down. Okay, and look, I can also add up. These are real numbers here. This is from 2004. Is equal to the number of deaths among females from heart disease is equal to 12,000. Number of deaths from males from heart disease is equal to the sum of all these deaths, which is 99. Okay, so the crude mortality rate for females due to heart disease is equal to the number of deaths in 2004 over the population of females in 2004. Okay, well, you know what happened there is that I got to take that and I got to multiply by 100,000 because it's rounding and you don't see it. It's a small fraction. Okay, it's 300.2 per 100,000. Okay, I'm going to do the same thing over here. For males, it's 9,900 divided by 3 million. There's fewer males as it happens. I'll multiply by 100,000 just get them into the same units. You don't have to multiply by 100,000. If you go into Excel and tell it to give you the actual decimal places, you can work in decimal places if you want to, but it really is so much more convenient to do it this way. Okay, so let's take a look at this. What's the crude mortality rate for females due to heart disease is 300. Crude mortality due to heart disease for males in New York City is 262. Oh my goodness. We just proved that females are dying more females are dying from heart disease in New York City than males are. Well, what's wrong with that? Everything I've read tells me that males are more susceptible to heart disease than females are, that they're protected for a large part of their lives for hormonal reasons from heart disease. Well, how did I get this wrong? Anybody want to volunteer a reason why this came out this way instead of what we expected? Right? Why do you think it came out that way? Right. Not differential diagnosis. That's good. I like that. That's great. But in this case, that's not really what happened here. What happened in here is how many males do we have that are over 85 in New York in that year? 35,000. How many females we have? We've got 87,000. How many do we have between 65 and 84? We have 500,000, but we only have 325,000 males, right? 920 in middle age. We got more in middle age and more younger ones. We have females are an older population. They live longer. So there are more elderly females than there are elderly males. So what happens is we see more deaths due to heart disease among females because there's just more older ones, right? Not because they're dying faster, right? The real thing we have to look at is the death rates. The age specific death rate from 25 to 44 for females is half what it is for males. Again, half what it is in middle age for males and females. It's still lower, 65 to 84. Even 84 and above, the age specific death rate is lower. The problem is that the number of deaths that we get are based on the population distribution, and these numbers are based on the populations of males, and this total number is based on the population of females. So what we need to do to get rid of that bias is that we have to compare these to age-specific mortality rates to the same population. So now, what will I choose as a single population to compare them to? You can compare them to the sum of the two populations. Let's take, in other words, the overall population in New York. You could take another population, another city. You could almost use anything you wanted. This seems a rational way to do it. I'm going to take the population of females in that age group plus populations of male in that age group. Hit enter. That's the total number from less than 25. Okay, so now I'm going to fill down let's see, this is 1, 2, 3, 4. I'm going to fill down 5 extra boxes. 1, 2, 3, 4, 5. I'm going to say fill down. Oops, I didn't need this. Oh, yeah, it worked out okay. That's the total over there. This is 85 plus. I'm not going to fill in the others. Okay, these are the total populations, male and female. Now I'm going to apply the age-specific death rate for females to this population and get an expected number of deaths. Okay, and then I'm going to apply the age-specific death rate for males to the same population and get an expected number of deaths. Okay, so what's the age-specific death rate for females? Here it is right here. These numbers right here are the age-specific death rates per 100,000. So I'm going to copy that in there. What's the, oops, what did it not like? What did I do there? Oh, I know what it did. Okay, I'm going to hit escape. This is based on putting it over. Actually, it should have worked. That's okay. I don't care. I'm just going to take this. I'm going to say edit, copy. Then I'm going to go over here and I'm going to tell it to paste. It's 5 boxes. Edit. I'm going to say paste special. I'm going to tell it just to paste the values. Oops, where'd it go? Oh, here it is over here. I'm just going to tell it to paste the values. See if that works. Yep, that worked. Okay, I'm not going to bother with trying to figure out why it didn't work first time. Now the age-specific death rates for males is over here per 100,000. Okay, and I'm going to say edit, paste special, just the values. Oh, okay. Yeah, I think that worked. Funny color, but it worked. Okay, so now, how many deaths would I expect among females and males? But we're going to take their age-specific death rates and apply them to the same population. instead of two different populations. Okay, so let's see how many females I would expect to die. I expect out of 2 million females, I would expect, okay, divided by 100,000. Remember, I got to get, that's per 100,000. I'd expect 46 deaths. So I'm going to go down there and do that for all of them. Fill down. Okay, that's the number of deaths I would expect. And the total number of female deaths, given this population distribution and size, is going to be, okay, 19,000, whatever it is. Now for males, it's going to be equal to this death rate times the same population in this group. Okay, and I'm going to fill down. Okay, and I'm going to, whoops, something went wrong there. Oh, I forgot the per 100,000. Okay, and I'm going to fill down. Okay, and I'm going to get the sum of deaths I expect there based on that same population. I'm comparing both of these death rates to the same population. So now let's see what happens now when I find the age-adjusted mortality rate for females and the age-adjusted mortality rate for males. Let's see what it comes out to now. Equals the number of female deaths is this, divided by the total population. If that were really the size of the population, that's actually, if I go by, if I multiply it by 100,000, that's going to be equal to that times 100,000. Okay, 244 per 100,000. And for males, it's going to be equal to this number of deaths, right, over the same population. We're comparing everything to the same population instead of two different populations. So this is equal to this times 100,000. Okay, and we get 336. And now all is right with the world. And indeed, if you have the same population distribution, mortality rates for males are higher than they are for females from heart disease. Okay, and now that we applied the age-adjusted rates to a single population that we chose, a lot of ways to choose that single population, but instead of applying these rates to two different populations, right, one which could be older than the other, we're now applying them to the same population. So now we can see that there's the real difference in death rates is that males die at a higher rate if the populations are the same, population distributions are the same than females. Okay, little complicated. It's not complicated. It's just a little tedious, right? Okay, so I'm going to call it a night. We've been at it for quite a while. I hope that helped. Anybody have any last second questions? Good luck on the exam. Maybe I'll if you email me some questions, I'll post some answers. Okay.